Hello, everybody. Welcome. My name is Jesús Espino. I'm principal engineer at Mattermost, and I'm going to talk about understanding the memory model of 5 different languages. Well, I work for Mattermost. That is open source alternative to Slack. We focus on mission-critical communication and all that stuff. But the thing is, we focus on stability, security, and all that stuff. Why I'm talking about that? Because I'm going to talk about memory models, about some foundational knowledge that is normally useful whenever you need stability, especially because when you are at a scale, the performance play an important role in stability. The last 4 years, I've been interviewing candidates for Mattermost, and one of the questions that I was asking was, what is the difference between the heap and the stack? And I was shocked about the amount of engineers with maybe 5 years of experience or more that didn't know what is the difference between the heap and the stack. Even they weren't unable to articulate anything around that. What is okay? I don't think it's necessarily common knowledge or something like that, but I was shocked, and I did want to fix it or try to help there. And that's the reason why I'm going to talk about all that. I'm going to start talking about the heap and the stack in general terms, and then we are going to jump into specific languages. So yeah, let's jump in directly. What is the heap? Sorry, what's the stack? The stack is exactly that, a stack, a pile of things. You can imagine the stack as a pile of things, but a pile of what? Basically, imagine these 3 functions here. You can have one function that is that has 2 values, 2 local variables, another that have another 2 local variables, another one that have 2 local variables. If I call the first one, what is going to be created is what is called a stack frame. That is a chunk of memory. It's a block of memory that is going to say, hey, I need 8 bytes of memory for this stack frame because I have 2 local variables that are in 32. That means that have 4 bytes each. So the compiler already knows that it needs 8 bytes. So it's going to take that stack size, that the stack frame is going to start using that. And if inside the call x, the function x, you call the function y, what is going to happen is you are going to create another stack frame that goes on top, or in this case on the bottom, of the other one. In this case, the stack frame is just bigger because this is 2 different sizes. Well, it is in 32 and in 64, so it's going to need 12 bytes. So it knows upfront that it's going to reserve that chunk of memory, and whenever call y finish, that gets popped from the stack. And you call the function seed, and it's going to override that chunk of memory and put that thing where was the previous one, and it's another stack frame there, and that is 16 bytes because it's 2 in 64. And finally, whenever the call x finish, call seed finish, pops from the stack, call x finish, pops from the stack, and if you call y, it's going to just start putting things on the stack again. So it's kind of growing and shrinking, and overriding things. That's super cool because of course, whenever you finish, it's finished. It's super cool because the stack is self-cleaning. It's super fast. It's super easy to manage. It doesn't need any garbage collection or something like that. Okay, let's talk about the heap. The heap, it's kind of a chunk of memory, a huge amount of memory that is out there. And you have to ask for a chunk, and you have to free that chunk eventually. So this is an example. You, for example, say, hey, I need 32 bytes for this variable x. So you ask for that in the heap. Somewhere in the heap, you get a pointer to somewhere in the heap that is reserved for you. And then whenever you finish, you free that. Okay? If you allocate more, you can allocate another thing. You can allocate multiple things in the heap. and whenever you finish using them, you free them, okay? It's easy peasy. Okay, let's see that with some code here. This is a pseudocode. It's suspiciously similar to Go. That is my language of choice, but it's pseudocode, so it's not necessarily Go, okay? If you call this function main, what it's going to do is it's going to see that there is a X variable here, that's the local variable that it has, and it's going to say, okay, I need a stack frame to store that X variable. So it's going to create the stack frame for that X variable, and it's going to call, in this case, it's going to call sum. Sum is going to reserve another stack frame that is going to have two variables, X and Y, and whenever it returns, remove from the stack and set the variable of X. And finally, it's going to call println that is going to override the previous stack frame. Okay. And whenever it finishes, it's clean everything up. What's the thing is, the stack is self-cleaning, doesn't need garbage collection, doesn't need anything. It's super fast. It's way faster than using the heap. You don't need to worry about freeing or not. So why don't we use a stack for everything if it's so amazing? Well, the stack has two problems. One of them is if you start, for example, if the sum function that we saw before return a pointer to a value instead of returning the final value, what is going to happen is this. You have the stack frame, you set the seed value, and you return a pointer to the seed value, and that's what is going to happen. It's going to have a pointer to something in memory that is no longer available. Actually, in fact, here probably is available because the implementation of the stack normally doesn't clean the bytes there. It's just wait until it gets overwrite. But the problem is, as soon as you call this println, it's going to create another stack frame, and it's going to just put garbage there. So it's not going to be, this pointer is going to be pointing to something that probably is not the right thing. So that's one of the problems of the stack. The other problem is whenever you don't know the size of something. If I want to create a list of elements, and that list is, I don't know, a random amount of elements size, how in the hell I allocate the stack frame? What is the stack size that I need? What is the size of the stack frame that I need? You don't know. So the way that it is solved is using the heap. So let's see an example of using the heap. Again, this is more clear that it's pseudocode and not Go, because I'm using malloc and free here for everything, and Go is a garbage collector language. So whenever you run main, in this case we have the size, the list, and the X values that are the local variables. So I get the size is 38, for example. I allocate a space for that size in the heap, and I get a pointer, and then I start looping over that's for loop, and I start setting values 0, 1, 2, up to 38. And then when I finish with everything, I free that. So that's how the heap is done. So let's start talking about languages. We are going to go through 5 different languages. We are going to talk about manual garbage collection, manual memory management. That is the model that is used in C. Ownership and borrowing, that is the model that is used in Rust. It's pretty unique. Reference counting, that is used in Python. Mark and sweep, that is used in Go, and mark and sweep generational, that is used in Java. So I'm going to go through all of them, trying to show some examples. I don't going to go much through the manual memory model, because the manual memory model is exactly what we have seen so far. It's you do mallocs, do frees, is all your responsibility. In C, basically, everything goes to the stack. So if you want something in the heap, you have to call malloc and you have to call free. There are libraries that are going to do that for you and things like that. But at the end of the day, you need to call malloc and you need to call free in your code, somewhere in your code or in your libraries. And the heap is used for dynamic size and for things that survive to the function call. So let's talk about Rust. I love Rust. It's a very cool language. Actually, the concept of how Rust manage memory is pretty smart. It's something in between manual memory management, but done through the compiler. So what Rust does is all the static size types normally goes to the stack, and everything that is dynamic goes to the heap. So for example, if they have structures that decides that what goes to the heap, there's a box type that is saying that what is stored in this box goes to the heap. So there are some types that are defined to go to the heap. But apart from that, what Rust does that is really smart is defining ownership of variables. So whenever you have a variable, that variable has an owner. Imagine that you have a list, and that list has an owner. You can give the list to another function, or you can lend it. So if you give the thing to another function, the other function is going to be the owner now. And you are not going to be able to use it again because it's no longer yours. If you lend that to the other function, if you pass a reference to the object to other function, you are lending it, and it's not the other function responsibility. It's your responsibility. It's still your responsibility, that variable. So knowing who is the owner of the variable, Rust can inject the mallocs and frees accordingly to that. So it can inject a free at the end of the function that owns the variable. So that's pretty amazing because everything is done in compile time, and it makes the Rust memory model work with similar to a garbage collector language, but without a runtime, with a garbage collection, with all that stuff that have other implications. So let's see an example of that. Imagine that I have this vector that is a list in Rust, and the stack frame is going to look like this. It's going to look like this list variable is going to contain a len capacity and a pointer to the value, to the heap's data, and then the x variable that is used in this loop. If I start doing that, whenever I start creating the list is going to be a 0 capacity, 0 length. It's not going to be modified yet. This is an implementation detail about lists in Rust. If we start the loop, the first iteration of the loop is going to be the x value is going to be 1, and it's going to start pushing to the list because it's going to push something to the list. The list is going to create some space in the heap, update this pointer, and point to this. The next iteration, we have x equal 2, and we are trying to add that to the list. This is an algorithm very common in list management. It's almost identical in Python and Go and probably a lot of other languages out there. But basically what it's doing is doubling the size of the space that it had before and adding the element. Well, copy over all the data and adding the element. And the next iteration is going to be 3. And because there's no enough space, it's going to double the size again. You can see now the capacity is 4 here, but the length is 3 because I added the element 3. The element 4 doesn't need duplication. And the element 5 duplicates again, and the element 6 is added there. So that's how Rust is doing that under the hood. But the interesting part here is whenever you finish the function, it's going to clean that up. You don't need to call free or something like that because the myfunc function is owning that variable. What happens is I pass that to other function, and the other function I give that to the other function. I give that as a value. So that is giving the value to the other function, And the other function is going to call this, well, it's going to receive that, it's going to point to the same space in memory, it's going to do something, and whenever it finishes, because other function was the owner, it's going to remove that. It's going to remove the stack as every function whenever it finishes, and it's going to remove the space in the heap. And then you try to do other stuff. But what happens if, the problem is you are here and you still have a pointer to a memory address that is not valid anymore. If I try to use the list here, what is going to happen, and that's one of the most amazing things about Rust, it's going to give you a compilation time error. It's going to say you, hey, you are trying to access something that is no longer available. It's outside of the lifetime, so you are not able to access that. So it doesn't matter if this is pointing here, because it's not going to compile anyway. So let's see another example. If we pass a reference to that variable, what is going to happen is that is pointing to that, and whenever it finishes, just clean the stack, because the ownership of the variable is not the other func. This my func is the owner of the variable. So I can keep using it here, and the compiler is going to be okay with that. And whenever it finishes, is then when that gets freed. So that's Rust, that's ownership and borrowing. Let's jump into reference counting in Python. Okay. Well, reference counting is a different approach that what it does is automatically count the number of reference of the objects. For example, if you create an object and then add that object to the list, and you have the variable pointing to that object, and the list element, one of the list elements is that object, you have to reference to that object. So the reference counting of that object is going to be true. If you start removing that reference, somehow removing from the list, or the variable is no longer accessible because you finish that function, then the reference counting reads 0 and gets removed. That's the whole idea behind reference counting. And reference counting imagine this scenario here. You have a lot of objects, they have references to each other, and for example, you remove this reference here. If you remove this reference here, this object is no longer reference counting 1, it's reference counting 0, and I can remove it. Not only that, it's going to remove this reference here, and it's going to remove this reference counting. So now it's reference count 1, and so on. This can propagate and can remove a lot of objects during the process. Okay, but what happens is, for example, I remove this reference here. This reference here is going to lead to remove this reference counting to 1, but still have a cycle there. Then what happened? Almost all the reference counted garbage collected languages out there use what is called a cycle collector that is going to search for these kind of cycles and try to break them and try to see if that cycle gets removed. Okay, let's see a bit of code. For example, here we have this. In Python, almost everything goes to the heap. Only pointers goes to the stack. So this is, for example, my functions have a pointer to an integer that is in memory and is in the heap, a pointer to a list that is in the heap, and a pointer to another integer that is in the heap. So that's the whole idea of that's how it's done in Python. So it starts creating this size that is going to point to that value. As you see in the heap, the value have that reference counting. This is an oversimplification, to be fair. Actually, the value 6 is not going to be reference counting 1. It's going to be reference counting maybe 300 or something like that, because in Python, the integer values from 0 to 256, I think, it's pre-cached, so they are pre-created and things like that. But this is an oversimplification. Don't take that as true, hold it as true. But the idea is, I'm trying to explain the concept anyway. Okay, the list, I create the list there, an empty list, and it's created here. I set the X variable to value 0, and I start looping over. It's the same process that we saw in Rust, but what I want to show you here, and I think is interesting, is whenever you add the first element, it's going to be added here, it's going to allocate this block of memory here, it's going to be added here, and it's going to point to this value here. This is a pointer to this value. So the reference counting now is 2 because X is value 0, and this value here is value 0. As soon as I iterate over again on the loop, the X now is value 1. And it's going to go here. It's reference counting 2, reference counting 1 here. So it's going to be changing over and over. And the final status is this, where you have a lot of 1 reference counting here. And whenever it finishes, what is going to happen, and I'm going to show you with this because red is not very clear. What is going to happen is this here, it's going to be the size. It's going to go, whenever the function finishes, it's going to be 0. These values are all referenced here, and this value is a reference in the stack. Okay, whenever I finish, the stack is going to move this to 0, this to 0, and because this is 0, all this gets removed, and then propagate here, and all these get to 0, and they all get freed. So that's the idea of how Python does the heap and the stack. Let's see an example here with other example. The stack does this. We create the stack frame for 3 and 4. We add 3 and 4. We call add. Because we call add, now we have 2 more references there. And I create seed. I return, if you see here, reference counting 2, reference counting 2, reference counting 1, this is seed. And whenever I finish, seed is no longer reference because I'm not storing anywhere. So reference counting is equal to 0. It gets removed, and the other ones get to 1. So, and eventually it's going to finish, and it's going to remove everything else. Okay, so that's how reference counting works. Let's go into the more advanced memory management systems. We are going to talk about the Go mark and sweep. Mark and sweep in Go, specifically the algorithm used for mark and sweep. There are multiple algorithms for mark and sweep, but in Go is used the 3-color mark and sweep. The 3-color mark and sweep is an algorithm for doing the mark and sweep process concurrently. Okay, let me explain first what mark and sweep is. Mark and sweep, the idea of mark and sweep is you explore all the data that you have in your, you explore the variables that are in your system and mark that ones that are accessible from the root. I'm going to explain what the root means. You mark that are accessible from the root, and everything else is not accessible, because if you can't find a path to them, means that that's no way for you to use that. So the idea is that you mark what is accessible and sweep what is not. Also, well, mark and sweep in Go, 3-color mark and sweep. I'm going to explain what it means. And also is a stop the world garbage collector. Stop the world means that there's a phase, there's a point in the garbage collection process that is going to stop everything else in the system. It's going to block the whole system and do something in only one single thread. Only one single thing is going to be happening at the same time in the program. So that's the stop the world. That stop the world is needed in most of the garbage collectors. There is some very advanced garbage collector, for example, in Java. You can plug a non-stop the world garbage collector that they have. I don't know, maybe probably they have more than one, but I know that they have at least one. But in the case of Go, it's a stop the world garbage collector. So, okay. Okay. Let's talk about what is how the tricolor algorithm works. The tricolor algorithm means that you have black, gray, and white. White means the node hasn't been checked yet. Gray means the node has been checked, but the children doesn't. And black means I have checked the node and the children. So how the mark phase work? It starts with the root. But what is the root? In Go, at least, the root is all the global variables. So it's going to check all the global variables. That's going to be one of the possible initial states, the possible initial variables, and all the stacks. In Go, you have one stack per Go routine. So it's going to check all the stack of all the Go routines to search for reference to objects in memory. And once you check all the globals and all the stack, you have the root. You have what are the variables that are referenced from the root. In this case, you have, you check all that, and you have these three objects that are referenced from the root. So now they are in gray because they have been checked, but the children hasn't. So if go further and they are gray, and whenever you try to check the children, you see that the 4 and the 5 is already black because it's already entirely checked. Then the same for the 7 and the 2 and the 3, and the same for the 6 and the same for the 1. And what you have here is some objects that are not referenced from the root, so you can sweep them. So let's see an example of this in Go. Imagine that I have this main function that is calling main function. You have the stack frame. The stack is going to work exactly the same for almost every language. So I create a random size here. I create a list. The list is a dynamic object, so we don't need to specify the size. So we start appending things and the same behavior that we've seen before. But check it out. It's not removing this. It's going to double that. It's going to keep adding elements. It's going to keep doubling, and all that stuff. And suddenly, at a certain point, the garbage collector runs for whatever reason. There's some reasons for the garbage collector for running. But, well, it runs time to time or in certain scenarios. The garbage collector runs and start checking the stack frames, and check the first stack frame, the one from the main function, check the second one, and see that, hey, I have a pointer here to this. So I'm going to mark this as, okay, this chunk of memory is used. But all these 3 chunks of memories, I don't have any reference to them, so I'm going to remove them. The reason why it's not cleaning up the old versions of the slice whenever it's growing is because implementation detail of how Rust manages slices. So Rust share the underneath array of slices between different slices. That's the reason why they are called slices, actually. Okay, so let's keep going. The sweep everything that is not referenced, and it keeps going, and it does whatever it needs to do, and suddenly, at certain other point, the garbage collector comes again and starts checking the frames and finish, and this is not reference to this, so I'm going to remove that. And that is how the mark and sweep garbage collection works. And to finish, I'm going to jump into mark and sweep generational. Mark and sweep generational is something that there's multiple languages out there that implements that, but I'm going to talk about Java. Okay, sorry, this is Java. In Java, you have this, it's exactly the same idea of mark and sweep. I'm not going to get into the details of mark and sweep, but the difference is adding the concept of generations. Instead of deciding that something is referenced or not, and sweeping what is not referenced, what it's going to check is something is referenced or not, And whenever I find something that is referenced, I'm going to keep it, but I'm going to do something else too. In Java, whenever you create a new object, it is created in a space in memory that is called the headend. The headend is the place where the new objects are created. So you create objects here in the headend, and one of them was created and dereferenced. It was a transient object that was like created and discarded very quickly. That's what is going to happen with most of the objects in almost every language. So that's the reason why this generational approach makes a lot of sense. So imagine that the garbage collector phase passed. So this one got removed, and all these ones here, the ones that was existing in the headend, it's moved to another part of another section that is called the survivor 0. The survivor 0 is still in the young generation, but it's not dead and it's different. So we keep creating objects, we keep dereferencing objects, and garbage collector passes and remove this thing here and move from the headend to survivor 0 and from survivor 0 to survivor 1. And finally, we create more objects and reference some of them, and the garbage collector pass and move things around. And this object here reach what is called the tenor, or the old generation. The old generations are a section in memory that store the old generations. They are objects that are old enough to be more or less sure that it's not going to be dereferenced so quickly. So headend, survivor 1, and survivor 0 are going to store almost all the transient objects, and they are going to be removed quickly. And the tenor section is going to store objects that are more long-living objects. And the whole point of this is that the garbage collector checks the young generation very often, and the old generation, it's going to be checked less often. So that way, it's a huge performance improvement in garbage collection. So that's it. That's all the memory models that I want to show you here. And why I don't need to show anything else, because if you understand all these models, you now can understand all these other languages, how they manage memory. Well, probably the C++ is the craziest one, because there's so many ways of doing things in C++. In C++, you have the manual memory model. You have some kind of ownership reference counting thing using smart pointers and things like that. But well, C++ is a beast. So in C# or .NET framework, you have mark and sweep generational. So now you know how the memory is managed in C#. Erlang is mark and sweep generational plus reference counting for what is called the shared heap, that is for inter-process communication. Fortran is manual. JavaScript is mark and sweep generational. I talk about Java, but when I talk about Java, it's the JVM, and the JVM is mark and sweep generational. So any JVM language is going to be using this garbage collection. By the way, Java, probably most of you already know, but Java have pluggable garbage collectors. So you can change the garbage collector from the mark and sweep generational to something else that is, for example, a non-stop the world or something like that. So you can play around with them. Julia, it's mark and sweep generational. Lua is mark and sweep generational since version 5.4. Before that was, I think, mark and sweep. I think they added generational later. Pascal is manual. PHP is reference counting. Perl is reference counting by Roku. That is the Perl 6 version of the language. It's mark and sweep generational. R is mark and sweep generational, Ruby is mark and sweep generational, and Swift, and this surprised me a lot, it's reference counting. And yeah, my expectation with this is now you are able to see, oh, this language is using this kind of memory management model. Now I understand how it works. For certain languages that can impact in the performance and things like that. For example, I work a lot with Go and understanding how the memory works and how what goes to the heap and what goes to the stack is very relevant for performance. So I hope this is going to be helpful for some of you. And that's it. Thank you. And if you want to talk with me about whatever, doesn't matter. I'd love to talk about foundational knowledge of these kind of things, but I'll talk about Go or about Maramos, about whatever you want. Feel free to reach me. And yeah, questions?
Thanks a lot for this very interesting talk, because it's nice to have a reminder, as you said. My question is about the generational garbage collecting dynamic. Do they include in the algorithm the size of the object also? Because you talk about age, but does size matters for garbage collecting? Do you know if they prioritize by size also, because it's important?
Yeah, I don't really know. I'm not an expert in Java, unless in the garbage collector. I know how more or less works in Go because it's my area of expertise. But no, I don't know if the size of the object matters. Probably have something there, but I will be lying. So
thanks.
As Go is your main language, do you know why Go doesn't go to generational collecting?
Yeah, I think I'm not 100% sure because I wasn't in the conversation. But as far as I know, Go is a not moving garbage collector, and the non-moving part means that it's not moving memory around. Would have certain implications, especially in the complexity of implementing things or interacting with other languages like using FFI or things like that. So it's I think that was a compromise there. The door for generational garbage collection is not closed, but the garbage collector of Go is really, really, really fast. So unless there's something that screws the garbage collector and needs to go a step forward, probably it's not going to change soon. Yeah.
So, as a follow-up question, is there a compaction of the heap in Go or not?
Sorry,
is there a compression or defragmentation of the heap at some point?
No. There's something that is not exactly compacting. What is done is in Go, it's used something that is called the memory allocator that defines that how the objects get stored in the heap. For example, in Go, all the heaps, all the objects that are, for example, 8 bytes are going to be stored together in the same page. And whenever that page gets freed, or there's no more objects in that size, is going to swipe that, or if we're going to reuse that if there's some objects of that size going there. So it's there's some algorithm there to not make everything scattered, but it's not a compaction process.
Thanks for the presentation. You said that in Java we can switch the garbage collector. Are there other languages that support this kind of thing?
I don't know any other language that support that. I think it's very. I don't know if it's unique to Java. I guess it's not. I guess somebody else do that, but I haven't seen in any major language doing that. But again, I'm not an expert in every language out there. So, but yeah, it's kind of it's a hard thing to do to make the garbage collector pluggable, because there's some complexities in the language itself that if you know exactly how the thing is going to work, you can make the things easier. But yeah, I don't think there's many languages that does that.
Thank you.
Okay. Okay. Thank you, everybody. And if anybody have any other question, feel free to reach me and we can talk.